G'day, this video is the first of two videos which focuses on series and parallel circuits. The core syllabus content that we're focusing on today is dot point 4.2.4. We're continuing electricity and magnetism, and our focus is still on inquiry question 2, which looks at the transfer and transformation of energy in electrical circuits. Dot point 4 is all about qualitatively and quantitatively comparing series and parallel circuits. Now, this is something that you would have started to do in either year 9 or year 10. But today we're going to start to take some extra steps in focusing on quantitative relationships that describe the behavior of components which are wired in series or parallel. Primarily today, our focus will be on Kirchhoff's current and voltage law. The other two formulae in this dot point will be covered in the second circuits video. So our key learning intentions today is to first review circuit diagrams as well as how we construct series and parallel circuits, and then begin to apply the conservation of energy as well as the conservation of charge to series circuits and parallel circuits respectively. When we look at the conservation of energy in series circuits, we begin to apply Kirchhoff's voltage law, and when we apply the conservation of charge to a parallel circuit, we apply Kirchhoff's current law. So just a couple of quick things on circuit diagrams. There are some key conventions that we need to follow when constructing one of these diagrams, which display electrical components in a circuit. In the table on the left, I've just provided a quick key which shows various simple electrical components. You may find that some components could have some alternate symbols, but this list more than covers the components that you'll need to be mindful of in the scope of this module. Particularly, things to focus on in a circuit diagram is that we need to have a power supply. Usually we just show a cell like this, where the thick, shorter line represents the negative terminal of the cell, and the long, thin line shows the positive terminal of the power supply. However, there can be some other alternate symbols. Some are listed here. Generally speaking, a simple symbol like this will usually suffice. We then have wires, which are shown as straight lines. Generally, when drawing wires, everything needs to be at right angles. And then as well, in these circuit diagrams, we'll have various symbols which represent components. Some of particular note include ammeters, voltmeters, light globes, as well as resistors. When constructing circuits, we can either be wiring components in series or wiring them in parallel. Again, this should be revision from year 9 and 10, but there are some simple definitions here on the side that we'll use to apply to some of these diagrams over here. So first off, our series circuit. All components are connected one after another or end to end. This forms a continuous loop from one terminal of the power supply to the other. Of our three diagrams, this one here demonstrates series best. In this case, we have a light globe, a resistor, and an ammeter, all wired one after the other to form a single continuous loop from one end of the power supply to the other. For a definition of parallel circuits, it says that all components are connected to form multiple pathways for charge to flow from one terminal of the power supply to the other. In our diagram on the left, there are two clear, distinct paths that charge can follow. And thus we consider this circuit to be parallel. Note as well that in the final diagram that I have here, I've put this one up to demonstrate that when we do construct circuits, some components may be in series with each other while other parts are in parallel. So in this example, we have three components all in series, all a part of the same loop, an LED, a resistor, and an ammeter. However, there is a second path for which current is able to flow through the voltmeter, meaning that the voltmeter has been wired in parallel to the rest of the circuit. When observing series circuits, we can also observe that energy is being conserved in the circuit. And this concept can be linked to Kirchhoff's voltage law, which is an application of the conservation of energy. Now, the law of conservation of energy states that the total energy of an isolated system remains constant. Energy can neither be created nor destroyed. Rather, it can only be transformed or transferred from one point to another. Now, this concept can be applied when focusing on voltage because voltage is a measure of potential or potential difference. And that can be summarized as V is equal to delta U on Q. In other words, the change in potential energy per charge. So in a series circuit, if the law of conservation of energy is being obeyed, then effectively there must also be a conservation of voltage. In practice, what that means is the potential difference of the power supply must be equal to the sum of the potential difference of all of the components in the series circuit. Now, mathematically, this can be summarized two ways. Either the sum of all voltages is equal to 0, or the total voltage of the circuit is equal to the sum of all voltages of all of the components in series. So in a scenario where the power supply was a 12-volt power supply, this would imply that the 3 light globes which are present in series should all have voltages which add up to this 12 volts as well. So for example, the first globe could have a potential difference of 5 volt, the second could have a potential difference of 4, and the last light globe might have a potential difference of 3 volts. Now in this case, V1, V2, and V3 all add up to the total voltage of the circuit, or in other words, the total voltage of the power supply. One way of thinking about it is that as a charge goes through each of the components, its potential will end up dropping based on the amount of potential difference. So as charge goes through the first component, there'll be a drop of 5 volts. As it goes through the second component, there'll be a drop in potential of 4 volts, 3 volts, and so on. These drops in potential as we go along should add up to the total potential difference from the beginning to the end of the circuit. Note here as well that in a series circuit, the current should be constant. The rate of flow of electrons should be the same the entire way through. In any scenario where we do have a circuit in series, this assumption is extremely important to hold. Things do get a little bit different, however, when we look at parallel circuits and how they behave. Here we can apply the conservation of charge to form Kirchhoff's current law. Now, the conservation of charge states that the net charge of an isolated system will always remain constant. What that means in a circuit is that as charge flows around the circuit, there's no gain of charge or loss of charge. The charge just continually moves around and around and around the circuit. However, in a parallel circuit, there are multiple pathways that the charge can actually take. And as a result, the current that flows through each pathway in the parallel circuit will not be the same as the total current or the total amount of charge that flows at the beginning of the circuit out of the power supply and at the end when it goes into the power supply. So if charge were to flow out of the circuit at multiple paths, the charge will have to take one of two options. Some amount of current may split off at the beginning, we'll call that I1. The rest will continue on ahead. Some of the current will then split off at the second junction, we'll call that I2, and the rest will continue along. And then in this example at least, there is one final third path that current can take. In this example, we'll call it I3. Now, as current moves across the circuit, they all join back up again and come back to our negative terminal. And here, this would be reflective of I total again. So for this example, let's imagine that we place an ammeter after each of our light globes to measure the current of each of the parts in the parallel circuit. According to Kirchhoff's current law, we could sum all of these up to come to I total. This would make 0.4 amps. And if Kirchhoff's current law is being upheld, if we were to place an ammeter at the end of the circuit, we should be able to see that the total current should amount to 0.4 amps as well. In these scenarios where we are working with parallel circuits, it's also really important to assume that voltage is constant. A couple of other things to quickly note as well. First off, this is probably the form or equation I would recommend that you use, that the total current, or in the case of Kirchhoff's voltage law, the total voltage in a series or parallel circuit, depending on which law you're using, is going to be the sum of the currents or voltages for all of the components or all of the pathways in the circuit. Notice that here, when we say all of the components and all of the pathways, we can show this by suggesting that we add on and on and on and on and on until we get to the last measurement, the nth measurement. So that could be the second, third, fourth, fifth, sixth component, or second, third, fourth, fifth, sixth branch in the parallel circuit. Kirchhoff's voltage law, as well as Kirchhoff's current law, both state that the sum of all voltages or the sum of all currents is equal to 0. This is technically true. However, it does require us to define either the total or all of the components as either negative current or positive current, or negative voltage or positive voltage. This can be a little bit tricky to sort of resolve at times, and probably adds a little bit more math that can lead to some confusion. And so as a result, I wouldn't recommend relying on this law too much, because it's going to require you to implement correct polarity. It's probably a lot more effective to be using the second versions of these voltage and current laws. Thank you very much, everyone. In the next video, we're going to look at applying Ohm's law to both the voltage and current laws that we've just learned about in this video. When we do that, it will begin to describe how resistances work in series and parallel circuits. But until then, have a good one.